Okay, welcome back. So the deflection of trusses, like I say, you go through, work out the force in each member, use that formula, PL over AE, to work out the change in length in each member, getting a new length, and then it's just a matter of drawing out the truss with the new geometry. Okay. And you know, when you say here that DE, for example, gets longer, make sure that when you draw it and you do, you know, if you give me coordinates of that, that it actually is longer. Okay. When you come to do it, if you do it with geometry method, you know, one way you can do it is sort of assume that's horizontal and then work out what this triangle is, and then rotate the whole thing down, because that point obviously is fixed in the horizontal direction. Sorry, vertical direction. That's the same. That's a fixed point. That is a fixed height. Everything else goes and moves from there. Okay. So if you wanted to start off saying assume that's horizontal, then you'd actually get something going up like that, and then you just have to rotate the whole thing down a little bit. Okay. Or you can draw it out in AutoCAD first, make sure you get the right answer. When you give me coordinates of something, and you give me a coordinate there and a coordinate there, make sure that length matches your new length over here. Okay. So I'll share a trade secret with you. In marking, the first place I go is I add the, because CF is almost always stays pretty close to vertical. So I just check the vertical components of CF and see whether it matches the new length. Then I know immediately if you're on the right track or not. Okay, all good there? Okay, cool. Let's move on to, what are we, deflection of beams, is that right?
Statically determinate beams.
Statically determinate beams. Very good distinction. Let's explore that first. What is the difference between a statically determinate beam and a statically indeterminate beam? No idea? Sorry, was that? Okay. Let's draw a statically determinate beam. There's a beam, there is a support, there is a roller support, and there is a force. That beam is statically determinate. Yeah. Hold that thought. There's our force for the next beam. I'm about to draw in a statically indeterminate beam. That same shape beam, same force on it, that is a statically indeterminate beam. Okay, do you know what that means? That is, yes, that is what we call a fixed end. Okay, so let's draw some reactions. Let's draw all the possible reactions on here that we can have in green, why not? Okay, possible reaction at a pin support is vertical and horizontal. There are no other possible reactions. Possible reaction at a roller support? Vertical only. Okay. Possible reaction at a fixed support? Vertical. What else? Nope. And horizontal. And bending. Should have put my rubber beam down here, I might go get it later. Possible reaction here, vertical and horizontal. Okay? Statically determinate means we can work out what all those forces are from simple statics and geometry. We know that the sum of the horizontal forces is 0. There's only one horizontal force. We know that some of the vertical forces is 0. We can work out by taking moments about either end or anywhere really. This one, we've got a horizontal force here, we've got a horizontal force there. How do we know that that beam is not being held in tension because it's got a massive force there and it's got a massive force there in the supports? We don't. okay, is statically indeterminate. We are not sure. See, that's a fixed support over there, it's pin support. This is a fixed end. Maybe when the fabricators came along and they put the beam here, they had to really stretch it to put it on the bolt holes there. And it's got this tension built into it. We don't know, there's not enough information there. That is statically indeterminate, okay? Statically indeterminate means you can't analyze it easily by hand using normal methods. You get to do that in second or third year. Does that make sense? So, statically determinate means you look at it and you go, I can solve all that, and you go ahead and you solve it all. Happy days. And if you work out that you just can't solve it all because there's too many unknowns, then you might be dealing with a statically indeterminate beam. Okay? That's obviously the hacker's way to work it out. In the topic you do, there's a formula of, you know, this many of members versus this many of those things, and it's honestly looks like a confusing way to me to work it out. If you look through and conceptualize this and think, all right, what happens if I take away one of these supports? If I say that is not there anymore, like take away the support, that is not there anymore, what would happen to that beam? Yes, it immediately falls over. Okay? If I say, all right, let's take away that support, what happens to that beam?
It should stay there.
It stays there because it's like, it becomes a cantilever, but it should stay there. Okay? If you can take away support and the thing stays there, it's statically indeterminate. If you take away the support and immediately the whole thing falls over, it's statically determinate. Okay? Let's see if I can give you another example. If I give you a truss, which is like that, and like that, okay, and give you that, and I give you that, and I give you that, like that. Okay, where that's all fixed in there, that's all fixed in there. Okay. Now, globally, as a whole truss, if you took away support, the thing would fall over, right? Okay, so globally, it's statically determinate, but as a truss member, as a truss, what happens if you take out one of those members? If you took out that member, okay, the thing would still be stable, right? If you took out another member, it would still be stable. If you took out that, and that, then you'll be left with that. Is that stable or unstable? That's unstable. You've got to the point where that thing just falls over, and that, because it's not a triangle more, can collapse kind of into a different shape. Okay, that's when it becomes statically indeterminate. So you can say that's got a level of indeterminacy of 3, because that's how many members you have to take out, or level 2. If you take out any 2 members, the thing will collapse. Okay. All right. So statically determinate beams. And we'll take out this as well. So let's have a look at this, and we will also put a different force on it. Let's go through some theory first. Okay. If we have a beam, and whenever I draw a beam, just assume there's some support somewhere. Okay. Okay. For the rest of this tutorial, I will only draw statically determinate beams. Okay. All right. And let's put a force on that. If I draw a force like that, okay, that means I have an evenly distributed load or uniformly distributed load, UDL, over the whole thing. Okay? Let's give the value of 5, for example. Okay. So I've got a simple beam with a bit of an extension on the end. I've got a UDL, uniformly distributed load of 5. Everyone happy with that? That isn't the load, okay. First thing I want to do is work out the shear force diagram. If the shear force diagram, if I integrate that, I will get the shear force diagram. Okay? So I'll call that V. If I integrate V, I will get M, the bending moment. If I integrate the bending moment, I will get the curvature. And if I integrate the curvature, I will get the deflection, the deflected shape. Okay, let's step through each of those. I have a UDL, it's 5. Okay? If I integrate 5, what do I get? 5x, right? When you integrate 5, you get 5x. Hold that thought if you need to. Okay? So if I do a shear force diagram on that, it is going to look like, we're going to do it up to the support, up to there. We're going to start that as, that's in the x direction, from 0 to whatever that length is. Okay? The shear force diagram actually does look like that. We're going to have increasing shear as we go along there. And I've already made a mistake. Alright. We've got a reaction there, we've got a reaction there, so it starts off as a negative reaction and it goes up like that. Okay? And just ignore, hang on, ignore that again. We're going to ignore that bit for now, just for the argument. When I integrate 5, I get a fixed value, the constant at the beginning, and then I get a line sloping upwards at 5. Okay? Because the shear force is whatever that reaction is, that's that reaction there, and then it's going to decrease by 5 kilonewtons for every meter we go along, because that's 5 kilonewtons per meter. Okay? So 5 kilonewtons per meter, we go 1 meter in, we put 5 kilonewtons onto it so far. We go 2 meters in, we put 10 kilonewtons onto it so far. Okay? So that line there is a line of a slope of 5. Because I go 1 meter in, and that point there is 5 less than that point. Okay? Okay, if you're not getting this, just bear with me for a bit, and hopefully there's going to be a light bulb come on soon. Okay? Alright, bending moment. Bending moment we know is 0 at a pin support. Okay? And the bending moment is going to look like that. Okay? Again, just ignore this tail here for a bit. Now, does everyone agree that's a bending moment of a simply supported beam? Okay? We start off with 0, and the bending moment, at the point where that passes 0, is our maximum bending moment. Okay? That is 5x plus a constant. This is, what do you do when you integrate 5x? We're going to get 25 x squared, right? Plus whatever that constant was of times x. Does that make sense so far? Plus another constant. Plus C2. Call that C1, call that C1. Okay? So we have integrated from the load to the shear force to the bending moment. We're now about to integrate 2 more times to get from the bending moment to the deflection. Okay? So we'll skip down to the deflection, where the deflection again, we're going to have 0 deflection there, and we're going to have 0 deflection there, and that's going to give a basic shape like that. Okay? And the curvature is going to be minimum curvature, maximum curvature in the middle. Yeah, it's also that shape. All right, now, but just that's the deflection there, the important one. Okay, so conceptually, here's what's happening. We start off with a load, which is constant. In the shear force, as we work our way along the beam, the shear force changes a little bit by the amount of the load, okay? That's an integral. In the bending moment, we start off with no bending, and we have heaps of bending in the middle, and then we have very little bending by the time we get to here. So we start off, this is about how fast is our bending changing. It's changing, let's go back to here. How fast was our shear force changing? It's changing at 5 every meter you go along. So that's how fast that's changing. Now we're going bending. How fast is our bending changing? Our bending changes a lot. We've got a steep line here when you're near supports, and by the time you get to the middle, the bending's not changing anymore. In fact, it's flat right there, and then it goes up again, okay? And then, how much is, that's our shear force, this is our bending moment here. When we go to curvature, if we have lots of bending happening, we're going to have a big change in curvature, okay? When we have a big change in curvature, then we're talking about a deflection, okay? Now, if this looks too confusing, don't worry about it, we'll go on to an application, okay? All right. Normally, we start with a bending moment and we work down to deflection. We don't do 4 steps of integration, because that's just painful. All right. Can we do a problem? Can someone give me a problem? Relatively easy one. One from the topic, if you want. Yep. So it is a cantilever beam with a UD element. Okay. So this is one of the problems we have. It's a cantilever beam, and it's got a uniform UDL, uniformly distributed load. How much is the load? 12.
Actually, sorry, 11.
Kilonewtons per meter. 11. 11 kilonewtons per meter. And how long is this beam?
That's 12.
That's 12. Okay. Cool. So that from there to there, there's x. Make that the 0 point, and by the time we get to here, x equals 12. All happy? Okay, and our reactions are all here, and a bending moment in that direction. All right, let's do the reactions. What is the vertical reaction there?
Yeah.
Sorry? Down. It's a force go. We've got 11 kilonewtons for every meter. We have 12 meters. So all the downward force has to be resisted by this upward force.
121.
So it's 11 times 12, 121. Yes. Take the easy one, Jake. What is the horizontal one? Horizontal component here.
0.
0. Very good. Because there's no external force pushing this horizontally. So 0. All right. What is the M? This is a bit harder. To do that, we need to consider this whole force and where its center of action is, which is halfway along. And so that will be, I'll do it up here, M equals 11 times 12. That's the whole force. And then the distance to that center of action there, which is 12 over 2, times 12 over 2. And what does that equal? So?
726.
726 kilonewton meters. All right. 726. Okay. So we've got our load. I'm going to take that red arrow off, just to be less confusing. We've got our load, we've got our moment, we've got our reactions, everything's set to go, okay? All good? All right, let's draw our bending moment diagram. So we will do that. Oh, let's draw the shear force diagram first. V, shear force diagram. What does it start at? Actually, it starts at what the reaction is. So it starts at 121. Okay. What's the shear force going to be at this end?
121.
No, it's going to be 0 because there's no reaction at that end. So our shear force is in fact a straight line down like that. Okay. It goes from 121 directly down to 0. And if we integrated, it's 11x, it's got a slope of 11. In this case negative, but 11. Because every meter you go along, 121, if you go along 1 meter, it'll be 11 less than that, it'll be 110. And then go another meter, it's going to be 11 less than that, all the way along until it gets to 0. So that's the V. V shear force, okay? Everyone okay with that? Alright, let's draw the bending moment diagram. What is the bending moment diagram of this? What's it going to start at?
Zero.
Give me an alternative answer.
Not 0.
Not 0, yes, correct. Okay. Okay, it's going to be 0 at this end. At the free end, there's no bending. Okay? So I'll give you 0 there for free. I'm just going to redraw that black line more straight. Alright, we're going to have 0 bending at the end. What about this end? 726, very good. Alright, so we've got 726. Okay, 726. That's V there. Okay, this is M here. And is it going to be straight or curved line? Curved, from the back, curved, with all the confidence in the world. Yes, it is a curved line. It is a curved line like, let's do it in green. It is a curved line like that. Ah dear. Let's try again. I'll do again. That's better. Okay. So it diminishes quickly and it tails to the end there at 0 at the end. Okay? Why does it diminish quickly? If we think about the shear force is the rate of change of the bending moment. It changes a lot here. By the time it gets to here, it changes very little. That's why we have steep slope here, changing very little to there. All good? So that bending moment diagram, excuse me, we have to get an equation for that bending moment diagram. So let's go back to here and think of this as an equation. So M equals, it starts off with 121. No, sorry. Starts off with 726. Okay, that's what it is at the support. But then we can see it diminishes. So how much does it diminish by? If we look at that, there was our load, there was our X, and there was an X there. So it's 726 minus 11x minus 6x. Okay, that's wrong. Hold that thought. I need a squared in there. Let's do this differently. Okay. let's go back to the shear force diagram. The shear force equation is V equals 121 minus 11x. Okay, does that work? 121 when x is 0 is correct. When x is 12, V is 0. Okay, let's integrate that. Integral of 121 minus 11x equals 121x minus 22x squared plus a constant. Is that right? Seriously, I'm not good at integrals. Is that right? 3 at maths people, anyone? Yeah, yeah, good, okay. All right, that is our m, okay? And when x is 0, then m is 726. So c is 726. Okay, so let's go to our equation. M is 726 plus 121x plus, sorry, minus. I'll come back. Still going, cool. Plus 121x minus 22x squared. Okay, that is our equation for the bending moment. We have to be able to derive that. We have to be able to get to that step in order to work out the deflection. Okay? Let's check it. If we put in x is 0, we get 726, correct? Can someone put in x is 12 for me? Do 12 times 121?
I think there was a mistake early on. Mistakes early on.
It should be.
The 121 is 11 times 11, and then that's thrown off the rest of it. So that's 11 times.
All right, say that again. There's a mistake, right?
So the 121 at the start.
That's wrong.
Yeah, that's 11 times. That's 11.
Okay, so what should that be? 132, right?
Yeah.
Okay.
And then that's.
So that's 132.
Yeah, and then yeah. It should
Oh
be,
my God. Here we go. And so is that right or is that wrong?
So that's wrong.
That's
So
wrong.
726 is equal to 11 times 11 times 12 divided by 2.
Wow. Okay. I'm glad you're here and you fixed up because yeah, we'd screw up mightily if we continue at this point. So we're going to start again.